Schottky surfaces.
So thanks a lot, Peter, for the opportunity to give this talk, and of course also for this big work you put in organizing this wonderful event here. So what I want to present is a joint work with Oscar Brandlow, who is a senior lecturer in Queen Mary, Torben Schick, who had been my former master student and unfortunately now left for industry. He's working in data science, so I do understand that. And Alex Weise, who is a permanent senior researcher at the Max Planck Institute for Mathematics in Bonn. So in a nutshell, what I want to present is what these pictures here mean, how we produce them, and how we know that they really show what we see here, what we think they show. So the title already hints at there's something involved with Schottky surfaces, something involved with resonances, and some numerics. So let me start with reminding you of what these objects are. So a Schottky surface is a hyperbolic surface of infinite area, no cusps and no elliptic points, so no singularities. You can just stick throughout the talk to these two pictures, which means you have some kind of a compact part in the middle, and then you glue to that some infinite cylinders, like here. And you can also have a higher genus, so meaning a number of holes in here. So in any case, you will always have a finite number of cylinders glued to that and a finite number of holes. And finite might mean 0. And on this is a hyperbolic matrix, which I invite you to just ignore. So resonance, for defining what is a resonance, we look at the Laplacian, the hyperbolic Laplacian on these surfaces, and then ask for its resolvent, which means we subtract the possible eigenvalue here and then take the inverse operator. So for purposes of the things which we do, we need to split the eigenvalue in physical space. So it's always this s times 1 minus s, but also here, feel free to just pretend it is the eigenvalue itself. It doesn't make a big difference for the intuition behind all of that. What we want to understand is where these pores, these resonances are, how they are distributed in the complex plane. There's a lot of interest in understanding where these are from pure mathematical points of view. So they have a lot of applications, but they are, I would say, hardly understood how they behave. So for that reason, Borthwick started to do some numerical experiments on them, and he wanted to understand where these resonances are. So let me explain what these pictures here mean. So first of all, these are two different pictures. So the left side is one picture and the right one is another picture. So first let's talk about the left picture. What we do is we consider a surface as here in the upper corner. So we have something with 3 hyperbolic ends, and we take this little L's here, which are length of certain geodesics, so, sort of the last periodic geodesic you have before the cylinder comes. So we assume that all of these have the same length. These are these 12, 12, 12 down here. And then we draw the S. So this S here means, the picture here means the hyperbolic axis is the real part of S, and the vertical axis is the imaginary part of the S. And these all here are very small little dots, very much near to each other, so that it looks like that they form a line. But this is what our eye does here. So we have to draw these little dots in some way, so they need some space here. What is known from pure mathematical point of view is that these dots start somewhere. So here in our case, and then to the right of it, there are no additional dots, but to the left of it, there are many dots. So this here is the dot picture for this one situation. He was mostly interested in understanding what happens on the gap between no dots and dots, but of course, as soon as you see these pictures, you get more interested in, okay, what happens more to the left where you expect to have a lot of dots. The picture on the right-hand side is also a surface of this type here, but this time we have 2 equal L's and 1 L is slightly off. You see it here, it's a 12, 12, 12, 1 situation. Here you do see bit better that these are actually isolated dots. You also see these pictures are somewhat similar, but then also quite different. Okay, one thing I would like to ask you to keep in mind is both pictures here end at 0. So the real part of S is for the pictures is always bigger than 0. We will come back to that in a second. So let me explain what he does here. He used what is called the periodic orbit expansion. So how does this go? How do we calculate numerically these resonances? So what you take as a helping function here is the Selbig zeta function, which comes as an Euler product. So it's a product over all primitive periodic geodesics, so closed geodesics on your surface. Then you have an auxiliary additional infinite product, and then you just take this vector here, and this L gamma is just the length of the geodesic. So it's like a Riemann zeta, it's like the Euler product of the Riemann zeta function, but for a surface. It is well known that this converges when the real part of S is sufficiently large. So for the experts in the audience, it means at least the Hausdorff dimension of the limit set, and it has a holomorphic extension to the whole plane. It's been proven by Patterson and Perry already about 20 years ago that when we have a 0, so when S is a 0 of the Selbig zeta function, then it is a resonance, or it's there for trivial reason. So I also invite you here, ignore the second part, just pretend all zeros of the Selbig zeta function are indeed resonances, so those numbers we want to calculate. And so this result for us means instead of fiddling around with this resolvent and its meromorphic continuation, we can try to get the zeros of the Selbig zeta function. There's another step which we did here. We introduced, with using the Selbig zeta function, a lot of the geometry of the space instead of just considering only the spectral world we have on our space. As a second step to get more dynamics into the picture, one observes that one has what is called a trans operator, which is essentially an evolution operator of the discretization of the geodesic flow on X. The weight in this evolution operators depend on the spectral parameter S, so on this resonance we want to calculate. And we can then express the Selbig zeta function as a Fredholm determinant of these trans operators. One can write them down explicitly. I won't do it. It won't help for understanding. Just believe me, there is a precise formula for these trans operators. And then one tries to use this formula here. So this Fredholm determinant representation of the Selbig zeta function to get approximation formula for the Selbig zeta function. And this goes like that. We introduce first an additional value, Z, which then goes into the Euler product right before we take the e to the power term. It itself has a power which is reflecting, in a certain sense, the word length of the geodesic, which we consider. This Z also goes into the Fredholm determinant right before the trans operator. Then we can use the standard formula for Fredholm determinants, expressing this as the exponential after the log. And then we take the series expansion of this whole formula with respect to Z, so we just have a power series. So it comes again, this formula on the next slide. So we end up with a formula of this form up here, and we can exactly calculate the dns as in sort of abstract terms. So for the dns as, we have a recursion formula in terms of the traces of the iterates of the transfer operator, and each trace of an iteration of a transfer operator is itself a sum of what I would call elementary traces, so precise numbers we can calculate, but unfortunately there are exponentially many with a growing n. What we do then is we chop off, we truncate this infinite series at some n, which we like, and then have a finite series here, finite sum. We try to calculate the zeros of this, so we just approximate them in some sense. and use these approximated zeros as approximations for the actual zeros of the Seebeck zeta function we want to have. There is a approximation error, which is well calculated. You see here something I will explain in a minute. So you need to have a look both at the S and at the N. So when you want to ask, so what happens when the N either goes up in the plane or goes to the left, so has a decreasing real part. So you see here in the exponent, and when you have a negative real part, you have a problem with the signs here, so then you need to compensate for this negative real part, so the minus negative real part then is positive, with a higher n to get a smaller approximation error, and the same with when the imaginary part goes up, you have to use a much higher n to be able to approximate with this n squared, with a minus n squared in the first part, the n's in the later part here. Unfortunately, a higher n also means to involve a higher and exponentially higher number of terms you have to calculate. And this is exactly the reason why these wonderful pictures by Borthwick stop at the real part of S equals 0. He noticed in his numerics that he has problems in terms of computational complexity. It's just too many terms you have to handle to go into the negative part. And also he noticed that there is a numerical instability. So there seems to be some error propagation, which is caused by the recursion formulas you need in these calculations. So when you want to improve on these pictures, when you want to go beyond that, you need to find some way to overcome these two problems. So here's one way which we're attempted to use. It's done by Borthwick and Weich. It's based on an idea by Žitanović and Eckhart, who used this for flat situations. The idea is to use what is called the Venkow-Sloka factorization for Seebeck zeta functions, which allows you to split your one zeta function which you have into a product of smaller zeta functions. So and then in each product you need to have less terms so that in the full zeta function, the full product, you get the odd result. This allowed them to go slightly into the negative part. You have to be very careful with these calculations because of this error propagation you have in the negative real part regime. For the positive real part, you don't have this error propagation problem here. So it's been a wonderful idea, and you also see that there's a lot of things going on already here in the negative part, but it still has these old limitations. And then we found these work, and we thought about this, or what can we do, and we wanted to avoid to have too many of these iterations. We wanted to avoid the exponential number of terms, and we came up with a method which allowed us to go further. So I will first show you this picture. It's exactly the extension of this other picture, and you see it was worth the effort. There's still a lot of party going on in the negative half plane here, and there are new structures which you couldn't see before. So it was really worth the effort to put all these thoughts into it. So what do? We also start with the Fredholm determinant representation of the Seebeck zeta functions at the same starting point, but then we don't want to do this periodic orbit expansion, because we want to really avoid these recursion formulas, which are always dangerous in numerics. But we notice, and it's well known actually, that these transfer operators which we have here, they have an integral kernel. And this integral kernel, even though I didn't completely spell it out here, it has a very easy form. It's a finite size matrix, and every entry in this matrix is either 0 or it is of this rational function form. And the S, the spectral parameter, the resonance we want to find, only appears up here in the exponent. So there are a lot of things you need to be very careful if you if you want to do precise work with this, but I would just put all of those under the rug. What exactly is the domain here? What are exactly all these coefficients which appear here? So one can go through everything and put on every step a precise number and a precise set on this, but it's not really interesting. So what did we then do then? There are several ways to express what we do. From our point of view, what we use is the Nistro method to approximate now the Fredholm determinant, which means we take the integral kernel which we have and use a Gauss-Chebyshev quadrature rule to calculate it. This means then that our Seebeck zeta function gets approximated by determinants of finite size matrices, which are of this form up here. So this first here is a 1 or a 0, depending on the entry. And the size of the matrix depends on the number of Chebyshev polynomials you want to use. Then you evaluate your kernel at the well-known collocation points of the Gauss quadrature, the Legendre quadrature, which are just these numbers down here. You put in the standard weights, which is just 1 over n, and you get this wonderful finite size matrix. And another feature which you have then, you can parallelize calculating of these matrices. You will want to calculate this for many, many S's. And you see in the formula of the kernel, because the S only appears here in the exponent, you can reuse quite a lot of the formulas which you have already calculated after changing the S. This speeds up the algorithm quite well. So the algorithm which we used is something which is well known for quite some time. It has a really long history. I would like to advertise a survey article by Bornemann about this. It also goes by the name Lagrange-Chebyshev approximation or Galerkin method and several other names. It is used over and over in relation with Fredholm determinants and transfer operators. So here 2 pointers to recent literature in physics. It's by Dugave, Gülman, Kozlowski, who do quantum transfer matrices with that, or transfer operator numerics, for example, by Nielsen and Wormel. So the work where we really had to put in work in here is to say what are the actual spaces our operators should act on when we consider them before numerics, when we want to calculate error estimates. So I will briefly go over this. I don't want to bore you with all these details, so let me just summarize the amount of work which went in here and say, okay, the approximation error, so from the pure mathematical approximation, just substituting the infinite product Fredholm determinant Seebeck zeta function by a finite dimensional matrix. This has exponential convergence with growing n. This is what we did. There goes in a lot of functional analysis. That also you have to take care about the numerical error. And the good thing here is you don't have any error propagation. You don't have recursion formulas. It's the error is as the error for the Lagrange-Chebyshev approximation, so it's really good convergence. And then you still need to calculate the zeros of this finite dimensional determinant, matrix determinant, which we have here. Also these you cannot just guess, you have to calculate by some numerical method. We used Newton's method, which also has good convergence. So, and then you see we can go, these are some pictures here, we can go quite far into the negative real part here. So this goes to some minus 1.6. We could go further. We stopped calculating at some point. So this is a surface with one hole and one cylinder. You can also go for the other type of surfaces to the negative part. You can also go much further up than the picture shows here. The algorithm is really stable here. The method which Borthwick was using, the periodic orbit expansion, Borthwick also noticed here that it needs too much calculation time. It's just too complex when you want to have more than 3 funnels or more than one hole and more than one funnel combined. But with this kernel-based method here, we can do this without any problem. And you see, we see also here very much things which look like resonance chains. So also here we see quite a lot of patterns in. It was initially conjectured that that won't happen. The reason behind this conjecture was that the length of periodic geodesics are quite different, so one shouldn't expect that. But it seems to be more like a feature, as you see quite often in ergodic theory. When you look at small parts of your space, you don't see anything, you don't see any patterns, but when you zoom out, you do see good patterns. So we didn't stop at 4 funnels, of course. Here's a 5 funnel picture. We also calculated 6 funnels. You can go on. So let me spend a word on calculation time here. It's a program we can run on any type of computer you give us. And these pictures here we did on a 16-core machine, so it's an equivalent to 6 to 8 laptops, depending on what kind of laptop you use. So compare this picture to that picture here. This is 4 hours difference. So, and then in additional 4 hours, the picture was completed. So the algorithm is, compared to other algorithms, quite fast. There's also something in pure mathematics you're very interested in. This is what happens when the Hausdorff dimension of your space, which in other words, the first resonance is quite near to 1. So quite near to 1 means above 1/2. And here you see the first resonance in here. It is known from mathematics that between the first resonance and 1/2, there are no additional resonances, or they are on the real axis. You also see that quite well here. Here's a better picture where you see this even better. So this first resonance is almost 0.9, so it's 0.86. You see it up here. This dotted line here is 1/2. You see resonances coming in, trying to pass this 1/2 line, but being forbidden to even touch it. And the blue line here, this straight line here, this is where delta 1/2 is. There is a conjecture saying, or let's say asking, for that the first accumulation point in the resonance set should be at real part delta is 1/2. It's still wide open, and also from the picture we cannot say whether we should support it or not, but it might well be. And now that you have these algorithms to calculate a lot of these resonances, you can start to play around with this. So here's, for example, a picture asking for how do resonance sets of 2 different surfaces relate to each other. So the one surface you see here are the green dots, and the other one are the pink dots. There is some overlap, and they are also in both sets different things. So there's a lot of open questions here. And of course, there's also another question. There is a result saying there is a spectral gap, meaning there's this first resonance at the delta, and then there is a small gap in the space, so that there is no additional resonance with real part between delta and, so in this gap in your space. We try to see this numerically. We don't know yet if it's possible to see it. So here you have to turn around your head. The imaginary line is the vertical one, is the horizontal one, and the real line is the vertical one. And this straight line here is delta. So it's not clear from the numerics. You would start calculating here 0, and then you go down and you see, oh yeah, we see the gap, and then you calculate further and you say, oh, we are not so sure about that. So with this picture, I would like to end. Thanks a lot for your attention.